Okay. Hello, everybody. Hello. Hello. Is this loud enough? Cool. Hello. It's good to see you all again. As always, don't panic. I think I've maybe said enough on that by now every single week, but if not, just keep on not panicking. One thing worth noting is that assignment 1 is out and has been out for just about a whole week. How many of you have started on assignment 1? I hope every single hand is raised. I'm a bit concerned that they're not all raised. People have started on assignment 1. Is it fun? Are you having fun? No? Come on. Sheer terror. So I think certainly with most things in programming or in life really, it's sort of hard to get started and it's kind of hard to approach a problem at first. But once you've started making progress and once you've hit the point where your server is working and you can play around with the colors, it's like the most fantastic thing ever. I've got some great examples for you that I'll probably show you on Wednesday about like Mandelbrot color schemes previous students have made that blow my mind with how amazing they are. So I will hopefully show you those on Wednesday. But for now, so we had the practice prac exam on Friday last week. Hopefully you found it sort of okay. For a start, congratulations, well done. 200 people got full marks. I was not expecting that at all. Exactly 200, which is a nice round number, so good job for that. But 200 people, yes, so that's a completely fantastic effort. You'll be able to see your marks through the way you normally see marks on WebCMS or from Sturek. The prac mark is either available now or will be available very soon. So, fantastic work, people who got full marks. People who didn't, it was a practice, right? So you can practice, you can do the exam again in week 10, and then whichever grade of the practice run and the week 10 one is better, you'll get that grade. So, fantastic work for a start, but a concerning thing is it's really important to read the instructions and to follow the instructions. So, we said things like, if you're not there before, is it 4:30, I think, the cutoff time, you can't sit the exam. And we're serious about that. If you get there after the point where the first session students have left, you can't sit the exam, like, end of story. I mean, other things here, you should go to the room we told you to go to, not the one on your timetable, we've told you that. Some people left their corralling room. So we have the second session people wait in a room, right? And then when the first session people have left, the second session people can go to the labs. But if you leave your corralling room, like the people who did that, you're lucky that you got to sit the exam. If you do that again next time, you're going to be told, you've left, you can't sit the exam. Like, I'm sorry, you should have stayed in your room. And finally, I was a bit concerned about the people whose solutions used scanf and getchar. We passed you in an array or a string. So if you then scanned things in and overwrote that array that we'd passed you in, you wouldn't have gotten the right answers. So make sure you read the questions carefully, make sure you think about what you're doing, make sure you follow the instructions, make sure you don't cheat or anything like that. But to those of you who did that, well done, and to those of you who did that and got full marks, double well done. So let's talk a bit about structs. So just sort of going over the language again with structs. So structs are a way that we can group together related data of differing types. So things like you saw the student struct in lectures, where you could store information about a student, their ZID, their name, their marks, and so on. You saw the complex struct in the assignment so far, and last week's labs, I think. So storing complex numbers. And we refer to these individual pieces of data as the fields or the members of the struct. In the syntax, again, we have type def, so that we can give it a nicer name, struct underscore type name, the contents of it, and then the type name. And we talked a couple of weeks ago about the lifetime of things or the scope of things, and Jashank had those beautiful ASCII art diagrams that sort of worked and sort of went wonky. But values that are on the stack, so values that are made local variables inside a function, will only live as long as the stack frame does. So if you make a variable inside a function, once that function has returned, that variable no longer exists. And so we can refer to that as the lifetime of the variable. Once the stack frame no longer exists, so once the function's gone, the variable no longer exists. And I have a demo of this. Description goes here. As you can see, I copied the template when I was doing it. Cool. So to demonstrate this, I've got a function or a program that I've written that looks at experimenting with the lifetime of variables. So we're going to be working with an array. So we've got a function that we're going to implement to make an array. So this will this will make an array of array size, fill all the values with this initial value, and then return that array. And then we've got a function to go through and print it, so to go through every element in the array and print it out. So in order to write our make array function, we're going to start out by making an array. Right, so of array size. We're then going to fill everything in the array with this value, so fairly straightforward, and hopefully you're feeling comfortable with this as one of the building blocks of programming. This while loop concept of start I at 0, or whatever your variable is, while that's less than whatever size or the number of things we're going to do something, and then I++. So in this case, we're going to set I to be our initial value. We're going to go I++, so this will fill out our array with array size things of value, initial value. And at the end, we're going to return the array. And so if you remember, arrays are sort of like a pointer to the chunk of space in the stack frame of that function, if we make it like this. And so I can say return array, that's valid C syntax, that's a valid thing to do. This will return this array, or effectively a pointer to the chunk of memory inside this function. And then it'll put that in whatever function I call this from. So, and that's why it returns an int star, because it's returning an array, which is, or a pointer, which is a pointer to the, I'll stop while I'm ahead. So we can call this function like this. And maybe I want to fill it with 17s. It's a good number. And so what this will do, this will make me an int pointer called array, call my make array function, which is going to make an array inside this function. It's going to go through and fill the array with this value we've given it, and then it's going to return the array. So to prove that it works, inside my make array function at the end, I'll print the array out, so you can see that the array is full of 17s. Just to prove that it works. Let me try and put these side by side. Cool. And so we can see DCC is warning us, hey, this isn't going to work. You can't return the address of something in the stack frame that's going to cause problems, but we want to see those problems, so we'll just ignore DCC for now. And this is why, even though it says a warning and it doesn't stop it from compiling, it's usually a good idea to pay attention to what it's saying. So I've run my function, run my program, it does what we expect, prints out 17, 17, 17, 17. So you might think, okay, this is fine, it's worked, right? We've made the array in here, we've created it, we've filled it with 17s, it's all good, we've returned it. But let's print it out in here as well. So what do you think we're going to get when we call print array in the main function after we've called make array, but then we're back in the main function? Print twice. So print the same thing twice, print the 17s and then more 17s. Cool. Does anyone think it'll do something other than print the 17s? Nonsense numbers? I think those are the two options. It could do what we want, or it could print out random stuff that we don't expect. So let's compile this again. Cool. So we can see the first one works, 17, 17, 17. But then the second time we call it from inside our main function, it's giving us some 17s, but some garbage values here. And so this is because if you think back to the stack frame diagrams that Zhizhank was drawing in the lecture slides, we have our main function, and then when it calls the print array function, it gets the stack frame on top. And the array will be made in there, it'll have the values in there, and then it will return. And then the memory that was up there can be reused by something else. And so then when we call the print array function, that's going to go into the space of memory that had the make array function previously. And because it's been told, hey, you can use this memory, it'll just overwrite what was in that array with whatever values it wants to use in its own stack frame. Does that make sense? Little bit? Which bit doesn't make sense? All of it. Did any of it make sense? Can I draw it up? Yes, I was thinking I'd do that. So as to not waste time while I plug this in, turn to the person next to you, introduce yourself. If you know them, then pick someone else. And say how your Mandelbrot is going. So the most amazing part of it so far, the progress you've made. We will resume after this short break, short interruption. Okay. Hello. Shh. How many of you met somebody new? How's your new friend's Mandelbrot going? Fair enough. So, like I did last time, I'll record this on my tablet and then add it onto the web stream video afterwards. Cool. So, I'll draw up the example that we've got here. If I do it sideways, it's not going to be sideways for you, is it? Okay. So we have our main function stack frame. And so this is going to contain the local variables for our main function. What are the local variables we have in here? Do we have any local variables? Yep. This one here? Cool. And so in our main, I'll write down here, main. We get a little bit of memory set aside for our int star array. And then we're going to call our make array function. And so the computer's going to go, okay, you've called a function called make array. I'm going to put some more memory up the top here for it, like stack it on top like a stack of pancakes. And then I'm going to go into that and make enough space in that for all of the local variables. So in this case, we've got an array of size, array size, so make it a bit bigger. So we have array size, and we've effectively got like 10 slots there, so 1, 2, 3. So imagine each of those lines would fit another number. And then we've also got our int I. Maybe I'll try. Let me try. Maybe it'll make more sense if I also give in some memory values. So So I've written these numbers in hexadecimal. The real addresses would be much bigger numbers than this, but for the interests of fitting them on the thing, I've given these numbers. So remember, memory starts with 0 at the top, and then the biggest number, 0xFFFFFFF down the bottom. So this is like a little zoomed-in part of memory. So each of these numbers refers to a memory address. I've made them all be 4 bytes big because on a standard 32-bit computer, ints are going to be 4 bytes, and so something like a character would use like 1 byte of those 4 bytes, but the ints themselves will use all 4 bytes. And so in our main function, we said we have our int star array. So that's going to use like the first available free space. I'll make this bigger so you can see them better. So this spot here will contain whatever the value is that make array returns. And I'll write by the side, it's called int star array. But we don't know what the value is going to be until we've called the function, right? Because we're going to have the return value from the function. So we'll leave this one blank, and then we'll go into our make array function. So we're making int array size. So we're going to get array size lots of integers worth of space in our function. In the interests of not drawing 10 things in this box, I've got the ... dots. So I'll kind of draw like we've got this one, and this one, and this one, and then through to make 10. And then we've also got our int I equals 0 down the bottom. So this one here is our int I. This one here is our int array. So one that we can do, int I equals 0, so we know we're going to put a 0 into this piece of memory here. So does this make sense so far? Yep, we've got our memory, well, we've got a zoomed in chunk of memory with numbers that are not real numbers, but sort of equivalent to them. We've got our stack frames for each function. I'll make those lines a bit bigger. So this is main stack frame, and then this is the one for our make array function. And so the computer's going to go kind of line by line. It's got enough space for this one. It's got enough space for this one. It's given it the value 0. Now it's going to go through while I is less than array size. Array I equals initial value. And so we'll go through and run this. I is 0. So array 0 is going to be initial value, which is 17. So we're going to put the number 17 into this slot. And then we're going to go I++. And so let me get a smaller eraser. This means the number that wasn't I has gone from a 0 to a 1, because we've increased the value of I. Then we're going to go around again. I is less than 10 still. Sorry, 1 is less than 10. So we're going to fill array 1 with 17. And then we're going to go I++. I is going to become 2. And then 2 is less than 10, so we're going to go through again. Array index 2 is going to become 17, and so on. And this will keep running until I is no longer less than 10. And so this will be when I is equal to 10, because 10 is not less than 10. So I'll skip past that part and just say this is now going to have 10 in it. Cool, so with me so far? Making sense so far? Cool, and so now we're going to print the array out, which means, please hold for one moment. I can't zoom upwards more, but I can zoom downwards more. So I'll... So now if we go upwards in memory more, because we're calling this print array function, That'll give us a new stack frame that's just going to hold the one I. So this one here is print array, and this one here was make array. Cool, and so we'll go, this would have been is 100 minus 4, 9C, hexadecimal, hopefully. So in here we've gone int I equals 0. So we've got our int I over here. And this is going to have the value 0 in it. And then we're going to go through again. So while I is less than array size, print out array 0. Array refers to this array here. Can you see where it's gesturing? Yeah. So it'll print out this one here at this memory address, and then this one here, and then this one here, and so on. And the reason that's fine is because it's lower down in memory. Like, it's in the stack frame below it, so it still exists at this point. So even though like it's in a stack frame and we can't pass those through functions, we can't pass them down in the stack. We can't pass them to functions that have called them, but we can pass them to functions that we're calling. And so this is going to go through, I is going to be 0, it's going to print out this one here, I is going to be 1, it's going to print out this one here, and so on through to I being 10. Then it's going to return from the function, it's going to implicitly return because it's a void function. Was it a question? Nope. So it's going to return from the function, and then this memory is going to become available to anybody. I'll scribble it out to demonstrate that. And then we're going to jump back to our make array function here. We're finished doing print array, so we're going to return array. So what's the value that we're going to return here if we're returning array? I'll give you a clue. The answer is written on the tablet. Any ideas? So we're returning array, we're returning effectively the pointer to the chunk of memory. That chunk of memory being this bit. Yes, it's going to be the first address. So it's going to return this number 0x100. And so that's what it's going to put inside here, memory address 0x100, because that's, remember, pointer, the value of a pointer is the address that it's pointing to. And then our stack frame is going to go away. And so the red squiggle, like the memory is still there, the values are still there in memory, except it's now marked as this is no longer being used, you can use this for whatever you want. And so then when we call our print array function, our print array function is going to build itself in memory. I'll do it in blue to make it really clear. So it's going to build itself a stack frame sort of like here. Right? And so it's going to have the int I being 0 right here in the memory that the previous function, that the make array function was using. And then it's going to go through, it's going to go, okay, so I'm printing out array, so I'm going to go to array index 0x100. And I'm going to print out what's in there. And so at array index 0x100, there's a 17. And so it printed out 17. And then again, it printed out 3 17s. So these 3 17s in memory hadn't been overwritten. But then the next 17 that was in memory, that was in this slot here, has been overridden with this big number here for some reason by one of the functions. Probably by printf, I think, or by one of the other magical things in stack frames. But does this make sense so far? So when we call another function, it'll just go plonk on top of the stack frame of the function that it's being called by, and whatever was in memory there, like, too bad it's gone now. And some of it is still there. We can see some of it is still 17, but a lot of it has been changed and has been overwritten. Cool. Are there any questions about that? what a good question. Is this why we have to use malloc or calloc when we want to have something, make it in a function and then have it persist? Yes, exactly, and that's the second to next slide. How many of you have watched the lecture recording from Wednesday, out of interest? A couple of you. Was it okay the way that I did the overlay with the tablet and the recording? Cool, thumbs up. It's good to see. So, values on the stack will only live as long as the stack frame does, as you saw in the diagram. When the function returns, when that stack frame can be used by another function later on, the variable effectively no longer exists. The piece of memory is still there, but the value could get overridden. And will, mostly, as we saw. But with structs, we want to structure outlive a function, right? If we're making a function that'll make us a struct, it's important that we can actually use that struct when we return from our make struct function, for example. And so one way we can do it, called like the systems programming way, pass a pointer to the struct down. So like you saw in the example we just did, if we make a struct like this on the stack and a local variable, and then we call the init student function, passing it in a pointer to that struct, a reference to that struct, it can then refer to that struct like how the previous thing was able to refer to the array when it printed it out. And because this function's happening after the function that this is in, like it's going above, and so it's not going to overwrite this struct that's down here, if that makes sense. I won't do that demo because we covered that with the diagram, but I'll put the code up after the lecture. And while this does work, like it works as a one-off thing, right? If we had to change our code for some reason and change how it worked, we'd have to be really, really careful that everything that was using this was like called after this function. We couldn't pass it around to other functions that were below this on the stack. There has to be a better way, and surprisingly enough, can use dynamic allocation. So, like we saw, DCC gave us a warning when we tried to return the value that we made inside the function. It said, you can't do this, it's in the stack frame, you're giving me a stack address, it's going to be overridden. So it's illegal. The C programming police will come knock on your door and tell you off. But we can get around this by putting it somewhere else in memory, right? Putting it somewhere safe in memory. And we put this on what we call the heap when we use something like calloc or malloc or the other allocation functions. And we also have the free function, which does the inverse of that. When we allocate some memory on the heap, it's there forever until we free it. So if we look at the struct code from a couple of weeks ago that Jashank wrote, hopefully this is familiar. We had a student struct with a whole bunch of things relating to students, name, tutorial, and so on. Then we made our student S, and we passed in our, to the read student function, we passed in this address of S so that it could refer back to that student struct. But how would we do this without having to make it in this function, right? How could we have a function that made a student? And like we've touched on before, we can put it in the heap, we can dynamically allocate it, and then it'll be somewhere safe. To demonstrate this, so I've zoomed out really far so that I can draw kind of an overview of memory. So if you remember from Jashank's diagram, so we had the magic up here, some other stuff, and then the heap, which grows downwards, and then the stack, which grows upwards, and then some more magic. So this bit here that we have is a really zoomed in part on the stack. And so if we zoom in on the stack in memory, we have our stack frames that we saw before. But zooming out for a bigger picture, if we put things on the heap over here in memory, And when we malloc or calloc something, it'll end up in this section of memory, the heap. You can see that even when our stack frames grow, so when we have another function up here and another function up here and so on, they're never going to manage to overwrite the things we've put in the heap up here. Cool, and so we can do that by doing just that, using calloc to allocate ourselves a student struct. I'll call this make student, and it's going to take in nothing. So kind of the steps we want to follow here, allocate some memory, maybe fill in details about the student, and then return the student struct. So if you remember the syntax to allocate some memory, I thought I had the exact example here I could copy to make sure I don't make a mistake, but we should be all good. So we use the calloc function, and the syntax for this is the number of things and then the size of the thing. So in this case, we want to allocate one student, and the size is a size of our struct student. And so what this is going to do is this is going to give us, on the heap, on that bit up there in memory, just enough memory to fit one student. And then this will give us a pointer to that memory, so we have a way of referring to that memory and accessing it. And of course, we need to store that pointer somewhere so we can actually refer to the memory. And we do that by, I'll call it S, saying our student pointer called S is equal to the pointer that we get when we calloc this. We could optionally fill in some details about the student, so maybe we could, maybe we'll take in a student ID. And so you might think it's kind of silly to have like a make student function that just callocs the memory and then returns it and does nothing else. Conveniently in this, we can do things like pass in the values we want to put in there. So pass in the student ID, pass in maybe a name or a tutorial or a mark or anything. And then in this one function, set up that student struct to have those values. So we'll just do the student ID here. Is it called a student ID? Yes. And then we return it. So one thing that I've had a lot of questions about every time I've been involved with teaching this course is when do we use the arrow and when do we use dot? I know Jashank calls it stab, I call it arrow, maybe we're just different. I'm not a violent person, who knows? But I refer to this as the arrow, and you can refer to it however you want. Yes, thank you for that, Jashank. So in C, if you remember, when we want to set a value inside a pointer, we've got to dereference it, right? So if I had some, like, int star, p equals the address of A, like we've seen before. If I wanted to access A using this pointer p, I have to dereference it. So I can say something like star p equals 5, and that'll set the value of A to be 5. So we use the star to dereference a pointer and then to set a value into it. And so we could do that with a struct. We could go, give me the struct, so dereference this student struct with the star in front. So take this pointer and go to the memory that it points to, and then give me the student ID field of that, and set that to be equal to student ID. And these are equivalent syntax. We could do either of these. But the reason that we do the S arrow is because this is really annoying to type. And so they went, let's give you a shorthand way of doing that. So rather than having to specifically dereference S and then use the dot student ID, we can just go S arrow student ID. Cool, does that make sense? I'll put that in a comment. Curtis, did I get the syntax right? Did I get the brackets around the right place? Cool. He was looking a bit concerned. He was just tired, okay. We're all tired, yes. So we're using the letter S because I'm following on with Jashank's, being consistent with Jashank's way of doing it. And he's really bad at naming things. So you can call this whatever you want. You could call it like new student, for example. That's probably what I would have called it if I were doing this from scratch. We try to avoid having meaningless variable names. We want our variable names to convey some sense of meaning. And so in this case, by calling it new student, we can see this is the new student that we've just created.
One thing to be mindful of here is if you have a function that's called new student, if you then declare a variable called new student, you'll wind up having a bad time. The compiler will tell you you're trying to call a variable as a function, and that's not allowed.
Did anybody not hear what Jashank said? You didn't hear? So he said, calling a variable new student is great, but if you've also got a function called new student, and then you try to make a variable called new student, bad things will happen. In this case, the compiler will trip you up and say, hey, you can't do that. But in other languages like Python, you can quite happily do that. And so you can overwrite your functions with variables, and then when you try to call your function, everything explodes. So cool. So we've got our make student function here that we've just made. We allocate some memory. So we say, please allocate me one amount of the size of a student struct of memory. And that'll give me a pointer to it up in the heap. So in the memory diagram, we had the heap was up here, the stack was up here. It'll give me a pointer to a high up address like this. Then take that memory, dereference it, so go to, take that pointer, dereference it, go to that memory, fill in the student ID field with the student ID we've been passed in, and then return this new struct that we've been given. And so we could, let me just comment out all of this. Rather than making like a concrete student S or making a student S local variable, you can go student star S equals make student and then give it some Z ID. So I think there's somebody in this course whose Z ID actually is like 51 something and then 4 zeros. To that person, you have the most amazing Z ID. So if you're here, I like your Z ID. I saw it and I was amazed. Or something like that. And so this will then give us a student that has had the ZID field pre-filled to have this ZID in it. Cool. Are there any questions about that? So I think maybe let's do one more thing before we have a break. Is anyone in desperate need of a break, or can you do another 5-10 minutes? You're good? Cool. So, I did something bad. I forgot to free my memory. So, as Jashank has been saying, Newton's third law of memory management, for every allocation, there must be an equal and opposite free. So we've allocated some memory on the heap, but if we don't free it, it'll just stay there forever. And in this case, forever means until the program ends, because the computer is nice enough to go, oh, you didn't free this memory, I'll free it for you. But if our program are really large and we're running for a long time, so like if this was Google Chrome, and we didn't free some memory that we'd allocated, then Google Chrome would just continue to use more and more memory until you had to buy more RAM to be able to use it as your web browser. So it's very unfortunate having to buy more RAM to use certain programs. So we've created our student. We've done a calloc in here. Even though this doesn't say calloc in it, we know that this does the allocation. So in order to free it, we have to use the very confusing syntax, free, and then the name of the pointer. So in this case, our pointer is called s, so I'm just going to say free s. Does that make sense? Cool. Right, and so this is looking at that complex number struct we looked at last weekend in Mandelbrot. But I've done this with the student struct already, so the syntax again, make me a pointer to a complex number called c, calloc me the memory for one of these, and the size of it is the size of the complex struct.